Just getting started. Yeah. Good evening, everyone. Welcome to the episode 5 of IEEE CEDA Industry Insight series. Today we are featuring Mr. Pradeep from SanDisk. And before going to the speaker intro, I would like to call Mr. Sajal to address the gathering for 2 minutes.
Yeah, thank you, Vamsi. Hello, everyone. I'm outside Bangalore and my bandwidth is a little bit limited. That's why I'm not turning on the video. But welcome everyone for the Industry Inside episode number 5. I think this is our series which we are planning to conduct for whole year, one lecture every month. And basically, we have started with device, then design, etc. And today is the PLL DLLs, which is very important, uh, I would say, component of SoC. Pradeep will touch upon it, but I think please make this session interactive and ask your questions. Get connected with Pradeep. Okay,
Yeah.
and thank you, Pradeep, for accepting our invitation. I think when I'm thinking about this topic, I think you are the first person or the name which came to my mind, and I'm very glad, like you said, yes, in the first go itself. So
Okay.
looking forward to the session, Pradeep, and
Yep.
thank you
Yeah.
everyone for joining again. Over to
Yeah.
you, Vamsi.
So going further, let me give a small intro about our today's speaker. Mr. Pradeep is a director of NAND analog design at SanDisk. Director of NAND analog design at SanDisk, and a semiconductor technology leader with more than 2 decades of experience in analog and mixed signal IC design. His expertise include NAND memory technologies, high-speed serial interfaces, PLLs, DLLs, and clock recovery circuits. Having held technical leadership roles across leading semiconductor companies, he has made significant contributions to the development of advanced memory and communication solutions. And sorry, Pradeep, sir, if I missed anything. And thanks for accepting the invite from the IEEE CEDA Bangalore chapter. The stage is yours.
Yeah, thank you. Let me share my screen. Okay, hope my screen is visible and I'm audible. Okay, we can start it.
It's pretty clear.
Yeah, okay. Okay, good evening, everybody. Thank you, Sajid, for extending the invite to me. So today I'll be going over an overview session on the phase lock loops and the delay lock loops, PLLs and DLLs, as we say. And these are the topics I'll be walking you guys through. Basically, I'll give you an introduction of these circuits, and then when it comes to PLLs, what are the components of the PLL or the loop dynamics, and more importantly, what are the design considerations when we design these PLLs, and what are the non-idealities on at the circuit as well as the silicon level we need to deal with when we are dealing with the PLLs. And also, I'll also similar topics I will be covering on the DLLs, which are the delay lock loops. Okay. So I want to use a PLL and a DLL, right? Before going deep into that, I want you guys to appreciate the problem for which these PLLs and DLLs are a solution, right? So mainly, first thing is the frequency generations on the SoCs, right? We all know we use piezoelectric crystals. We call them crystal as an oscillator configuration. We call them crystal oscillators to provide clean reference clocks to our chips. But we have practical limitations of that. They are kind of relatively low frequencies. We get with order of 25 to 50 megahertz, a typical crystal oscillator. So yeah, but our SoCs typically need in gigahertz of frequencies, right? So that is one problem we need to address. And also the clock distribution problem, right? When we have a huge SoC, we have a huge signal degradation as the clock gets routed to clock trees. It faces delays, queues, and it gets corrupted at every stage with the noise as it traverses through the time. So if we have a problem of, we have a problem of clock distribution where we need at different locations of the chip, the clock edges need to be aligned. Then these DLLs are the ones that act as a precise alignment tools, right? So basically, yeah, in a nutshell, PLL are for frequency multiplication or frequency synthesis, whereas DLLs are but mainly for the clock edge alignment. So this, this is this is the reason why we try to use these circuits. Right? So some of the real world applications, sorry, the PLLs, basically PLLs we use in, for example, in RF transceivers, right? You see like any RF front end, we have the signal coming in, we have RF amplifier, we call them typically a low noise amplifiers, and we have a mixer which we demodulate the signal before it goes to the baseband processing. So to demodulate a signal, then we definitely need a local oscillator signal which selects a channel which we need to down convert, right? So for on an RF transceiver, to generate the local oscillators before the signal goes to the baseband, to down convert them, we use a PLL to generate a high frequency and high accurate frequency clock source. Okay, and also in SoC, yeah, we use PLLs for multiple purposes. We have sometimes a network of PLLs where we have each PLL serving a different purpose, right? One of, say, like we have one common crystal oscillator, it goes to multiple PLLs. We have a set of PLLs which are, we have a PLL which is used for interface clock, where the PLL which is used for a system clock, okay, and so on and so forth. And also a lot of times to meet the EM regulations, the clock we generate, right, need to have some kind of a spectrum modulation and a noise shaping kind of thing. And we have a PLLs with those features also implemented on the SoC. Right? These are kind of a top key applications of PLLs. And if you go to DLLs, where we kind of use it, right? Mainly we use, with one of the very wide application of a DLL is on the memory interfaces, right? So we have a DQ data and the strobe signal coming into the die, and for a good good data integrity, right? We need to have the DQs, the strobe signal 90 degrees out of phase, right? For the best sampling window, right? We need the strobe signal 90 degrees out of phase with incoming data signal, and this delays typically need to be process temperature, right? And voltage independent. So we need a very accurate delay so that the edges are aligned for the best data capture window. So in these scenarios, we use the DLLs. It's a very popular application of the DLLs. Any memory interface, the receive path will have DQ and DQS alignment using a DLL. And also a lot of times, as I said, like the DSKU network, we to make sure that we have a clock at a source, and then it traverses through a clock tree, and at the end of the clock tree, you need the source clock and the destination clock to be edge aligned, right? We kind of keep this whole thing in a DLL loop, right? And there we control the delays such that we add a negative or positive skew, so that we have ultimately the clock tree at the clock signal at the destination will have the required edge alignments, right? So this is how we use DLL in a de-skewing kind of application. So yeah, what are the key components of a PLL, right? So as I said, so a PLL basically has a phase and frequency detector, right? And which outputs a digital pulses based on the phase difference between the reference clock and the feedback clock, okay? And the output pulse width is proportional to the phase difference. And then we have something called, we'll get into the more circuit level details of this in the next few slides. So the charge pump mainly converts the digital error pulses into an analog current, and then we have a filter which integrates it, right? And integrates it, the error current, to generate a control voltage to something called a voltage controlled oscillator. We call it as a VCO, right? And which is actually the main frequency generator in this whole PLL. And then give it into a feedback loop again to the phase reference detector. So this is what, so it basically compares the difference between the VCO output and the reference clock and tries to make it phase aligned. That's the whole charter of the PLL, what it needs to do. And as you can see, if you divide the output clock of the VCO by N and give it the same as FREF frequency, then effectively we'll get a frequency multiplication. So basically, right, the clock output will be N times the FREF, right, and which is the feedback division ratio. So this is how a PLL basically acts as a frequency multiplier or a synthesizer. Okay. So these are the key blocks. So more delving deep into voltage control oscillator, what exactly is a VCO? Is basically it gives the controlled frequency, right? A controlled oscillating frequency for a particular voltage. Yeah, we call it V control. So this is a kind of a application. We say like we have a static offset, even if with a certain initial V control, we have a static frequency at which the PLL keeps oscillating. So omega naught plus K VCO, which is called the VCO gain in the V control, right? So basically this VCO, we call it, we kind of spec it in terms of megahertz per millivolt or gigahertz per volt, right? So it is like, that's a multiplication factor. So let's say if it's 100 megahertz per 100 millivolt, that means every 100 megahertz variation in the V control, we give to the VCO, we get output frequency increment of 100 megahertz. But again, right, for any application that needs to be done, we should use the PLL. The V control has to be solid, right? It has to be in a steady state for it to operate properly. As I said, it's a direct one-to-one correlation or the multiplication of the voltage control. So any noise or any ripple on the V control will translate to the equivalent or amplified version of the frequency variation. Right? So that's right. So these are the kind, like, I mean, common challenges we have in the VCO is the programmability range, right? Let's say I have to generate at 1 gigahertz range with the available V control of 0.5 volt. So how do I go about it? So, and then also maintaining the noise limit, right? So as I said, if the V control is very high, the gain is very high, a very small noise itself gives a variation at the output frequency, right? If the KVCO is low, the gain is low, then to meet the complete frequency range, it will be a challenge within the V control range. So these are the kind of trade-offs we have to do, where these are the thought process that go into and trade-offs that we need to consider before we kind of choose what is the frequency we need to operate the VCO, and also what is the V control range. Go to next slide. So basically, how the VCO looks like, right? With the voltage control oscillator, widely two configurations we have. It's one is called, we call the CMOS ring oscillator, ROS, right? Where, so it is a 3-stage ring oscillator I have shown, where we have the delay cells with the required phase shift connected in oscillator configuration, so that we meet the oscillation criteria, right? So we have a 3 oscillator stages. They can be a ring oscillator stage, a CMOS ring oscillator stage, or a LC tank kind of a circuit. Okay, so these are 2 widely used types of VCOs in the industry, right? So each one has its own trade-offs and so on and so forth, right? So like ring oscillators, we get a very wide frequency range, right? And it's very easy to design and integrate in a SoC, right? And also we can very easily generate any number of phases, multi-phase outputs. And yeah, and we have, it occupies a much smaller area, but it's a higher power. You need to burn more power if you want to have very low jitter. Jitter is basically the frequency variation or time period variation. We'll come into those details later. Whereas an LC tank oscillator, yeah, it's a narrow frequency range, but it's very good in terms of the jitter, if the inductors are of a good quality factor, the Q factor. And also, yeah, but it's a really large area, and also we need a very good field solver tools to model the inductor, right? And also a lot of times the varactor models that we get from the fab are not that great. But yeah, but this LCVCO is very good in terms of the noise performance and the sensitivity. So these are again the choice of the architecture of a ring oscillator, right? The choice of a VCO is it a ring oscillator based and uh, LCVCO again depends on a lot of these trade-offs. And typically, right, I mean these days in the deep submicron technology, like our FinFET technologies, where we reach almost to 2 nanometer, we are able to generate a very high frequency even with the ring oscillators because the propagation delays are low. But yeah, like a few, maybe a decade back, and so when we were in the 60 or 135, 130 nanometer technologies working in that, right? So it was a kind of a thumb rule, like anything about 2 to 3 gigahertz oscillator, we tend to go to the LCVCOs itself because the ring oscillators were not that fast. The CMOS was not that fast to generate that kind of a high frequency. Okay. So I'm just touching upon how a VCO looks and how it operates more, right? Or some of, if you're interested, what are the kind of design considerations we take while designing VCO. So this is kind of a very popular VCO architecture, very widely used. We call it as a current starved ring oscillator, right? So it's a very controlled frequency. Yeah, we were like, we precisely control, I mean, intends to starve the current which goes into the ring oscillator, right? So the oscillatory frequency is regulated by limiting the current which we pump here. So we see that it's like here we control here, we current source generates and it dumps into the ring oscillator, and again, yeah, based on the capacitance, the C, dV by dt, the right, R on and C, right? The oscillator frequency is determined, right? But here, what you see, this kind of a configuration is kind of a very sensitive to be control. As I said, we don't want our KVCO. We want it to be optimum for our application. If the VCO gain is very high, then again, it is very sensitive to the input voltage variations and the equivalent frequency variations. So we kind of do a linearized thing. So it's source degeneration so that we get a good controlled V versus I characteristic, and we get a more linear frequency versus voltage characteristics. So those linearized current starved oscillator is kind of one of a very popularly used ring oscillator architectures in the industry, right? And again, right, is the number of stages, right? It can be, how do you choose, right? The number of stages when you go about designing a VCO, right? So it's again a trade-off between the frequency, power, and the phase noise, right? If you have more stages, right, the max frequency you achieve will get limited because the delay is more, right? And the power is more. But at the same time, when we talk of the noise performance, yeah, the more stages will have a more controlled KVCO, and it will result in a better phase noise. And also again, right, the transistor W well, because there are high-speed circuits, right? So now again, it's a trade-off between the amount of current you want to pump in, the speed you want to achieve. But again, you use a large W, for example, your R on, right, is R into C, right? Your R on will reduce, but at the same time, the parasitic capacitance which gets added at these nodes, which will again get increased. Again, that's a trade-off, right? You want a speed or a parasitic cap. That's why we choose that. We do multiple iterations to arrive at the optimal size of this W and L for this ring oscillator. So designers typically spend a lot of time in doing multiple iterations and arrive at the optimal. And with experience, you get more intuition, and we try to converge faster. Okay, yeah. And also length of the transistor, right? Again, a smaller L for the equivalent Rn, we have a smaller W, less parasitic cap. But again, if you use the very minimal L, we have a concern of the leakage current, correct? Which goes in and cause some problem. So again, yeah, these are like, I'm just giving a few trade-offs that we need to consider in the current star VCO design. And also, again, current control voltage range also, right? We need to have optimal control voltage range for optimal frequency range we want to achieve by this PLL with the VCO. Okay. Going to next slide. Yeah, so among the components we have gone through the VCO, then again, I'll just explain you what does the PFD means. That's a phase frequency detector, right? So it's, as I said, like it detects both phase and frequency differences, and output pulse widths are proportional to the phase error, right? So it's again like it's a lead and lag kind of thing, right? I just mentioned as up and down, right? So if the feedback clock is lagging in phase uh, to the reference, we ask the PLL to go faster or the VCO to go faster eventually, correct? So we call it as up pulse, right? And if it is leading in phase, if reference is leading in phase, we want it to be uh, slowing down, correct? So the way it operates is whenever the reference edge comes up, right, and then the up, if a reference edge comes up ahead of the feedback clock, the up pulse goes high, and whenever we get the feedback blockage, both of these get reset, right? And if I show you a scenario where, yeah, again, it is a rising edge detection. Here, the feedback clock is at a higher phase, then the down pulse goes higher, right? And then when we get the next up, the reference pulse edge, we get a reset pulse. Both the pulses will be reset. And again, next up and down pulse will be based on either reference clock goes high first or the feedback loss goes up. So we get these pulses, this behavior along the locking behavior of PLL. We get these pulses out at the output of the phase and frequency detector. How exactly we again translate it to the PLL VCO control voltage? We use something called a charge pump, right? Again, as if you can remember the loop here, right? We have PFD, VCO, and PFD charge pump. This is the loop filter and the control voltage, which goes to the VCO. So again, this up and down pulses are given to this current mirror network, which kind of charge and discharge this filter capacitor, which acts as the voltage control source for the VCO, right? So it is right whenever if you have the up pulse, it starts charging, and the moment the down pulse comes, both the up and down pulses are reset, the switches are open, and the control voltage stays high. Again, till we get next up or down pulse. When you get a next down pulse, again it starts discharging, right? And it goes down. So if you see, this is how the P control voltage, right, varies or charges and discharges, right, based on the phase frequency and detector outputs. So I just given an example here in a continuous for a few pulses or reference and feedback signals, right? How the V control voltage keeps generating here, as you can see. Correct. And one of the key challenges of a PLL charge pump design is like you, as I said here, right? We don't because in a lot of most of the time it is off, right? Both switches are off, and also when it is both up and down pulse are on, we don't want there to be any mismatch current between the charge pump and this. That's up current source, and the current source which is charging, and the current source which is discharging, right? Up and down current mirror, right? And also maintaining this mismatch, right, between the current sources across the voltage control range is also one of the challenge, right? We definitely tend to have certain mismatches because of this. So as we've seen, right, we have the charge pump. Just again a recap of the whole PLL circuit. PFD, we see the charge pump which integrates into the control voltage and the VCO, and it gives the feedback. So how do you model this loop, right? So it's, as you see, it's a closed loop system, right? So it has its own loop dynamics, right? So this is how we have a PLL open loop transfer function, right? 1 by n is the frequency divider, right? KVCO by S. KVCO is, as I indicated to you, is the VCO gain. We do it S because we are integrating the frequency, right, in a PLL, because we're comparing the phase but not the frequency, right? It's a KVCO by S. And also the charge pump IP by SC, because we have the loop filter capacitor, right? The main capacitor here. This is the looping capacitor here. But as you see, if you go to this, we have 2 poles at the origin by virtue of the open loop transfer function, the way it's behaving. So we need to add a 0 with using a R, right, to stabilize this PLL so that it becomes a single order, single pole approximation, right, till the unity gain bandwidth. So this is the transfer function of the PLL, and this is the omega 0 we had through R1 and C1, and this is omega C, we call it as any control loop, right, the unity gain frequency. Okay, so it starts from the 40 dB per decade roll off, and then when it encounters 0, the roll off reduces to 20 dB per decade. So these are the key loop dynamics. I mean, these are key equations to remember whenever we go about designing a PLL, right? So, and again, all these equations, these are kind of a thumb rule equations, right? All these equations are in terms of where here I've shown is we translated in terms of the PLL the component characteristics, right? IP is the charge pump current, KVCO is the VCO gain, N is the feedback division ratio, and R1 is the stabilizing 0, right? So we have this omega N, and then the omega C, the unity gain frequency. This we call it as a loop bandwidth of the PLL, right? We call it, we use this expression. It is nothing but the 2 zeta into omega N. So zeta is the damping factor, as in any control system. So how is the phase margin you want to achieve for the PLL again, right? You want to have a large zeta, you may have to have a very high capacitor and R1, and again, we may have a lot of your area limitations. And so these are all like, we typically use a lot of MATLAB or MATCAD models and try to play around with all these parameters to achieve an optimal loop bandwidth, optimal stability for the optimal loop bandwidth. So as in any control system, right, the PL like omega out, right, it's again, the control voltage shows the same behavior, so does the output frequency, correct? So it can be a over-damped system, depending on the zeta, a critically damped or under-damped system. You can choose the phase margin and tune it for that. Again, the main thing is settling time versus ripple of the V control, right? If you want to have a ultra-fast settling time, it's like kind of, but we have initial V control ripple. It reaches the range faster, but again, we may have a higher ripple, right? And also stability of the system we need to ensure. Yeah. So these are the key equations which we consider for determining the loop parameters or the charge pump current or all the PLL component characteristics when we go about designing the PLLs. And we have something called a Gardner stability limit when we go for a PLL design. So as I said, a very key component of the PLL, right? Okay, so go to the loop dynamics. We design the PLL for a certain loop bandwidth, right? That is one of our very key specification, the PLL loop bandwidth, and I will show you a lot of things that it impacts practically, right? How the loop bandwidth impacts a lot of things. So there is something called a Gardner stability limit. This is kind of a thumb rule we follow when we design the PLL. So the PLLs are basically a discrete time systems for which we have a linear approximation, right? Because we have a sampling charge pump which samples the phase. We have a PFD which samples the phase at discrete reference intervals, and we turn on and turn off the charge pumps, right? So if the loop bandwidth is too high, then there will be some sampling delays which may destabilize the loop, right? And we have this equation which is a very popular equation from a paper from Florent Gardner, we call the Gardner criteria. So if you are targeting for a zeta of kind of 0.707, we say the omega C or the loop bandwidth, the PLL bandwidth should be less than 2.3 times the reference frequency. So say if your reference frequency is, for example, 10 megahertz, your loop bandwidth cannot be more than 2.3 megahertz. But again, this is a criteria, mathematical criteria to be on a safer side. The kind of thumb rule we use in the industry is to call it as the rule of 10, right? So we call it the rule of 10. So to secure a very safe margin, right? Because again, it's a very, it's critically damped. Sorry, it's a critically damped criteria, correct? So we apply a very conservative engineering criteria. So we kind of go for, we call it as rule of thumb. As a thumb rule, we start with reference frequency by 10. So if it's a hertz, 40
हाइट से
megahertz.
ज्यादा स्पेस लगता है.
Okay, it's a 40 megahertz reference frequency. We keep it as at a 4 megahertz as a max loop bandwidth. But sometimes we have seen, we have went into design even going up to more aggressively, even up to by 5 also, because certain specs which the loop bandwidth requires, we cannot meet with the FRF by 10, right? It's advisable, but people tend to go even up to FRF by 6 or FRF by 5, but we typically don't go beyond less than FRF, more than FRF by 5, right? This is called the rule of 10 for that. Okay, so this is one design consideration, right? The loop bandwidth of the PLL. And also, as I said, right, one with a very important design criteria or a design consideration for the PLL is the jitter in the PLLs, right? So jitter is like it's a time domain representation of your phase noise or the phase variation, right? So the phase noise is kind of a frequency domain representation of the timing instability. Jitter is a measurement of the instabilities on the timing domain, right? So we have multiple kinds of jitter, right? We have multiple types of jitter, because if you open any PLL data sheet, we have they don't just mention as jitter, they mention is it a period jitter, or is it a cycle to cycle jitter, or is it a long-term jitter, right? And again, depending on the applications, the different kinds of jitter are critical, right? So a period jitter means like every period of the period, how much it is deviating from the expected ideal time period, right? So if it is 100 megahertz is the ideal time period, that particular clock cycle, by how much it varies from the ideal time period. Okay, so this is very crucial spec for if the PLL is used for clocking a processor, right? And then we call something called cycle to cycle jitter, right? Cycle to cycle jitter is like a frequency variation between two subsequent clock cycles of the clock, VCO clock. So again, right, Tn plus 2, n minus 1, this is one clock period, and again, the previous cycle was Tn plus 1 and Tn. So this kind of jitter is very critical when we have a chain of, we have kind of a chained logic where we have logic gates to need to be settled like in stages, right? So it is critical when one cycle to another cycle, the gates need to definitely settle before the next cycle is clocked. So in those kind of scenarios, we have cycle to cycle jitter. And long-term jitter is the accumulated jitter, like how much jitter it gets accumulated over n number of cycles, right? So let's say 1,000 cycles, PLL clock cycles have happened, and what was the effective cumulative time period of the 1,000 cycles minus 1,000 into the ideal time period. So this is a long-term jitter. So this is again, this plays a major role. This overall complete accumulated call it as long-term jitter. This plays a major role when we use the PLL for serial data communication. So depending on the application, the characteristic of the PLL which we need to target, right? The kind of optimization we need to do on the PLL, right? That varies. So this is the type of the jitter, and a lot of times we keep coming across the terms deterministic jitter and a random jitter, right? And so again, as the term says, deterministic jitter is something we can model, like it's in our control, or we know the phenomena. Like if there is a supply, like for example, usually the kind of noise that the supply induces, we call it is basically disagreement jitter. Like a certain noise profile, what is the supply rejection onto the V control, how much V control varies, and how much the frequency varies. So that it can be modeled and simulated and cross-checked, right? Yeah, transient simulation, right? So that's it. So the jitter, the cause of the jitter, if the cause of the jitter can be modeled and the jitter can be simulated using that, we call it as we can determine that, we call it as deterministic jitter. Random jitter is again, it's a very random phenomena. It is basically result of the device noise. So right, we call it as a random jitter. And also kind of, this is the type of jitter, this is the nature of jitter, and the magnitude of the jitter, right? So it can be sometimes called the peak to peak. What is the jitter? Or sometimes called, we define jitter as a root mean square value, called the RMS jitter. And sometimes we have a relation between how we convert RMS to peak to peak. So this gives the magnitude of jitter. So sorry, multiple sources of jitter in a PLL, like that can be because of VCO phase noise, it can be because of the reference clock noise. We come to most of these things in the coming slides, right? We call there is a dead zone in the PFD that causes some jitter, and the current source mismatches in the charge pump, right? And these are the key sources. Practically, when you go about design in the PLL, right? These are the key sources which induce the jitter on the controller in the PLL. So I kept on talking about phase noise, right, of the oscillator. So maybe do more, give you go more details, right, on the phase noise. So it's basically, again, we have a short-term fluctuations on the output of the signal. So if you go with a frequency domain representation, we call it as a phase noise. So it is basically, here you see, like, this is the carrier frequency, this is the offset from the carrier. So y-axis basically indicates the ratio of the noise power with respect to the carrier power at a certain frequency offset in a 1 megahertz bandwidth. So this kind of a definition of the phase noise, we kind of define it as a dBc per hertz. So dBc is a separation with respect to the carrier power and in a 1 hertz bandwidth. Okay. And what are the sources of phase noise? So this is a way to simulate this whole phase noise in a PLL, right? If you or using your cadence tool set, right? You have something called a pseudo steady state analysis and a P noise analysis for a cadence, so which we use for getting this kind of a graph. Okay, and what are the sources of the phase noise? Are basically the active device noise inside the VCO, right? We have a flicker and thermal noise region, right? There's a 1 by f cube, 1 by f square, and 1 by f noise we see here, right? And also the tuning sensitivity, as I said, like if the VCO is very sensitive to the control voltage, the gain is very high, right? It shows up in the phase noise plot. And if you count the LC VCO, LC tank, then the Q factor, resonant tank losses, right? Q factor is basically, as you know, the ratio between the reactance to the resistance, right? So if you have a low Q factor, the tank losses also contribute to the phase noise. This is applicable only for the LC VCO, not for the ring. This is for all the VCOs. So how do you minimize the VCO phase noise? As I said before, we try to have optimal transistor sizing. We have a minimize as minimal as possible tuning sensitivity of KVCO. We kind of maximize the Q factor it's an LC VCO. Again, all this come with a high Q factor or a KVCO. All this come with again its own area, power, right? Nothing comes for free, right? Area and power trade-offs. Okay. So how is the noise transfer function? Again, this is also one of the very key practical consideration of a PLL, right? As I said, we need to, the main spec of the PLL, when you go designing about a PLL, the first thing you determine is, of course, you are given a spec, right? You have to have a reference frequency of 40 megahertz, and somebody asks you to design a PLL which goes from 400 gigahertz to 1.2 gigahertz. That is just the spec given to you, right? And some top level other specs like jitter and all. That's it. But now, how do you approach in designing the PLL? The first thing you determine is what is the bandwidth I want to target for my PLL, right? Based on that itself, we know, correct? Based on that itself, we determine the other loop components of the PLL. So again, how we choose the bandwidth again is like depends on, before we go to how to determine the bandwidth of the PLL, we do the phase noise transfer function of the PLL, right? This is a closed loop transfer function. So we have two noise sources, one that comes from the input side from the reference clock. So this is the 5 out by 5 reference. We have the low pass filter characteristic for the reference frequency noise. So the noise induced by the oscillator, the VCO, right? It has a high pass characteristic. So this is the 3 dB bandwidth, or it is kind of low bandwidth, open loop bandwidth in the open loop. Okay, so this is the trade-off, right? So now the input phase response is low pass, and output phase response is, or VCO phase noise response is the high pass. So again, so again, right? So then it all depends on what kind of source is dominant, correct? What kind of source is dominant in your uh, PLL. So we do the VCO phase noise simulation and we do the reference clock phase noise simulation. If the VCO, most of the time, it's a VCO phase noise is more dominant than the reference, unless you're using another PLL to, or some on-chip oscillator as a reference to the PLL. If it's external crystal oscillator, the reference phase noise is floor is much lesser than the VCO phase noise. So if you want to have, if the VCO phase noise is dominant, we have a very, we'd go for a higher loop bandwidth. If reference phase noise is dominant, we go for a lower loop bandwidth. So we kind of add up both, and we kind of, as you see, there is a sweet spot where it is optimal, right? There will be optimal filtering of both reference phase noise and VCO phase output phase noise is achieved. So as if we, once we get the phase noise, right, we convert it to the jitter spec, right? So we design the PLL for a certain phase noise, and we have the jitter target as I mentioned, correct? So this is a phase noise plot as I have shown, right? So as I said, like if you do your analysis, right, a P-noise analysis in the pseudo steady state analysis in your cadence simulator, you will get a phase noise cost like this. So basically, we want to convert this phase noise to the jitter. So kind of do the area calculation, we integrate the phase noise, which is the area under the curve, and we have these equations again, where with which you can convert the phase noise into the targeted jitter, right? So before we can integrate the phase noise, is again just an oscillator phase noise. As I said, we apply the noise transfer function of the PLL to this phase noise. So these days we have a lot of tools and models to do this. So I think this might be aware. So this is the VCO phase noise. This is the reference clock frequency phase noise, right? For a certain loop bandwidth, right? You add, this is a filtered reference clock phase noise, and this red line is a filtered VCO phase noise. When you add up both, you get a profile like this for the integrated phase noise of the noise shaping is done by the PLL. And this area, this phase noise plot, we do the integration for the area under the curve and can translate it into the jitter. So again, as I said, you get some jitter spec from the data sheet or your system, right? We need to make it 800 megahertz, for example. I have to have an RMS jitter of 5 picosecond, right? So that is a spec, and this is the how you calculate from the phase noise. So what you do, you optimize you target some certain phase noise, you simulate, and you plug it in the mathematical model. If jitter is exceeding the spec, then what you do, you optimize the VCO design further so that this whole noise floor comes down, correct? So for example, here its attenuation is 100 dBc per hertz. If with 100 dBc per hertz and certain loop bandwidth, right, with the PLL we can achieve, you can't need the jitter spec. So you are getting, then you try to optimize the phase noise, right? Make this 100 dBc per hertz to some 120 dBc per hertz, right? And there is a limit beyond which you cannot do. So, and if that is not sufficient, we try to increase the bandwidth. But again, when you increase the bandwidth, the stability is tough to meet, right? Because again, phase matching has to be met. But increasing the bandwidth, the stability is not able to meet, or the VCO gain is not sufficient. Then we again try to go back and so there are multiple knobs, right? As I said, like this is a kind of a complex loop where we have multiple iterations. A lot of times we have to go by intuition, by design experience and practice. We get into this, correct? So there are a lot of variables. So which one to attack, the loop bandwidth or the phase noise or something. But as a thumb rule, like what I'm saying, my experience is say you typically target a VCO with a phase noise more than 100 dB to 110 dBc per hertz at 1 megahertz offset. That is kind of a good sweet spot. But on a ring oscillators, we cannot achieve more than that because of the device noise. Whereas the LC tank VCOs, we have seen can achieve up to 130, 140 dBc per hertz of phase noise attenuation at 1 megahertz offset. So that's the kind of advantage LC oscillators give over a ring oscillators, right? So again, yeah. So here I've shown how I uh, uh, how we simulate the phase noise, how we apply the noise transfer function, how we convert to jitter, right? So I have gone through the loop dynamics, how we determine that, and how we go about the jitter, right? So yeah, these are different things of a design. And one more spec we get for the PLL is the locking time, right? You keep getting the locking time of the PLL. Like locking time is nothing but you switch from one frequency to other, right? As I said, it's a synthesizer. I have switched the channel from 10 gigahertz to 9.6 gigahertz. This is the control voltage plot. So this is for a VCO where like the frequency increases for reduction of VCO characteristic, control voltage, so, right, or whatever. So, right, so when you switch from one division ratio to other, we have an n dividend factor, right? When you switch from one division ratio to other, what is the time it takes to switch from one PLL? So this is the lock time of the PLL. Some applications like a RF frequency synthesizer are shown in the example, right? We have to select different channels, right? So from 5 gigahertz channel, I have to go to 6 gigahertz channel, for example. So then the channel switching time has to be extremely fast, right? That's a spec for the system. Right there, then we have to make sure the locking time is very fast. And this is the startup time for the very first thing, right? And so then frequency band switching, we call it as a lock time, right? Again, high bandwidth results in faster lock times, better rejection of phase noise, and but low bandwidth again. If it's a low bandwidth, it's a better rejection of reference clock noise and reference pulse. I'll come to that later, right? And again, phase margin is something we need to ensure even at the high bandwidth. So, right. And also we have something called some other dynamic parameters called capture range and the lock range of the PLL, right? So when you when you enable the PLL, right, we have certain initial frequency which for the initial control voltage for which it starts oscillating at some initial frequency, but there is a certain range beyond which it can't acquire the lock. So that we have to be mindful. That is called the capture range or the pull-in range. Okay, so if let's say this is our whole lock range required, if the capture range or pull-in range is somewhere let's say since the center, if it is at this point, right, if the capture range of pull-in is not sufficient, then we may have to do some initialization or initial conditions for the PLL, right, to initialize it to a certain V control so that we get the pull-in range. So this is also one of the practical problems where sometimes we don't realize it in the simulations, but on the silicon we see that the PLL is not having any kind of capture range. And again, this is the whole range. It's in plus or minus, but the whole thing comes under the locking range. So if we have 400 to 200 megahertz PLL, this is the complete locking range. So yeah, so we have to be mindful of that. We can do some simulations and calculations and determine our oscillator sensitivity and all that. Okay. And also, again, we are one more thing is on the, as I said, the PFD, right? And also, right, we have phase and frequency detector here, right? We have some phenomena called dead zone of the PLL, right? Where dead zone of the PFD, sorry, PFD. So if if there is a reset pulse generated and both up and down are aligned, right? We need some width for the charge pump switches to turn on, right? So we add some certain delay to avoid the dead zone. Otherwise, there will be a range where the phase difference that the PLL can't resolve, it results in the dead zone. So that leads to a static offset where the PLL locks, which is not desirable. So we intentionally add certain delay for that. So if you, and also there are some non-idealities because I talked about oscillator non-idealities like the phase noise, etc. Right? Also talked about the PFD non-ideality. In terms of charge pump, also we have certain non-idealities, right? Where the up and down pulses are not matched. So when it's in the lock condition, right, we have a up current pulse with different and down current, And also there is across the KVCO range, there is up and down current mismatch, right? The down current is lower than the up current, right? So when this kind of a phenomenon happens, right, whenever there is this reset pulse widths, then the control voltage is charged up. And then what happens is, to compensate for that, again, the PLL locks with a certain phase difference in the lock condition, so that it discharges to a certain level and then it comes up. This is all within the reference pulse width. So this is a kind of a static offset and kind of a deterministic ripple kind of ripple that is seen in the lock condition of a PLL. So a lot of times we see it in the silicon too, right? Lock condition PLL, which is basically a result of these charge pump non-idealities. And also we have a phenomenon called, again, these all PFD and charge pump non-idealities, the leakage, the mismatch, they result in something called the reference pulse, because all these non-idealities repeat at a frequency, a PFD reference frequency interval. So if you see the spectrum, then we have the reference pulse at reference frequency and also the harmonics of the reference frequency, right? So again, certain applications like the RF synthesizers, right, they have very tight requirement even on the reference bus. So you kind of determine, right, the bandwidth based on that. So again, these are all the primary causes of the reference bus. Whatever non-idealities I have mentioned through, these are all the non-idealities that result in these reference bus. So mainly the PFD and charge pump non-idealities difference in the reference pulse. VCO, right, non-ideality is the phase noise part. So we have to kind of balance between these two when we go about designing the PLL. Okay, maybe I have a couple of more slides on the PLL. So are we okay on the time? I mean, it's only 5 minutes left. Is it okay we extend it to 15 minutes or so?
Actually, we need to have Q&A also.
Okay.
So accordingly, we can extend.
Pardon?
Sorry, we can extend it for 10 more minutes.
Yeah, no,
have Q&A session.
Yeah, that's what. I'll finish the presentation in another 10 minutes, and then we can have a Q&A. Yeah, I think I have.
Sure,
yeah. So again, so we have gone through all the PLLs, the non-idealities, the loop dynamics, and all the different characteristics, right? And as I said, PLL has multiple applications, and each application demands a different kind of requirement or specifications from each of this PLL, right? So for example, it's a wireless application, the phase noise and right signal purity is important. For a processor, right, it's stable timing, right? RMS jitter is more important. Sometimes for radar automotive applications, the linearity and lock time are more important, correct? The third is the capture range is more important. So again, each of these things, for example, it's handheld device, right? Or an IoT application, right? There, low power PLL is much more important, right? Sometimes it goes, it's you need to have a very, so there is a different trade-offs we do for that. So again, as I said, PLL has multiple applications, and depending on the applications, again, it's all very right. It's like not one size fits all, right? So we have to choose a configuration and the PLL loop parameters as per the application. So I won't go detail into this, but again, this is a design flow we use. As I said, like we determine the frequency range, right? For a bandwidth, we determine the AVCO needed for optimal phase noise, right? As I said, we first determine the bandwidth. After we determine the KVCO and the VCO range, we determine we set the bandwidth to FRF per 10, right? And the charge pump current, and we determine certain charge pump current for what bandwidth is needed. We calculate the loop filter values. These days you get a lot of tools for loop filter values to stabilize for that particular bandwidth with MathCAD or MathCAD. And on top of that, PLL, we keep tons of programming options, right? Because you see like what you simulate, what you get on silicon, a lot of times are very different. So overcome that, we need a lot of programming options in the PLL, programming options for the loop filter, because your mathematical modeling may be inaccurate. On silicon, you see it unstable, right? So we key product programmability for loop filter values for PLL loop dynamics. Again, sometimes you have to support multiple variable frequencies too. So for that also, and also we need to have a proper feedback division ratio also, right? So and again, like we also have, I'll just really go fast in interest of time. Integer and synthesizers, right? Let's say, for example, we have an application where as RF frequency synthesizer channel, right? I can have to have the clock frequencies in 1 megahertz or 2 megahertz steps to select the channel. So for that, if you go by integer synthesizer, integer range channel, the 1 megahertz, we need to use only a 1 megahertz reference clock. But if you have a low reference clock, we have a low PLL bandwidth. A low PLL bandwidth again has issue in terms of the phase noise filtering because it's a high pass characteristic and we cannot meet the jitter requirements, and that's a concern, right? So we have a concept, something called a fractional and PLLs also. I won't go much details into it, but it's the same phenomena as integer and PLL, but here what you do is, let's say 17 point, we have a sigma delta modulator that keep modulating the division ratio. So let's say like I have to have 17.5 as a division ratio. What I do is, or let's say I have to have 17.2 as a division ratio. I have 17 enabled for 4 cycles, and every 5th cycle the division ratio changes to 8. It's not as straightforward, but like a top level, so that the weighted average of that, right, becomes 17.2, right? Yeah, so that's the whole idea. Okay. Okay, yeah, this is on the PLL. I'll go really fast on the DLL. DLL is not as complicated as the PLL, so maybe I can make it fast. But again, this also has similar structure, but one key difference is it's basically just a delay line because it's just a phase alignment, right? So here, if you see, right, you have to just phase the delayed output, right? For example, like I'm going to have 1 clock cycle delay, correct? Output side has exactly 1 clock cycle delay with the input reference. So here, if you see, we just have a voltage control delay line where with the control voltage, we just vary the delays of this delay element, right? We don't have any feedback configuration as an oscillator, right? So this is the delay line. And this is also again a very popular architecture of analog DLL delay line, right? So where we have, as you see, we don't have any feedback configuration as in oscillator. So we again control the delay using the bias currents, using control voltage, and it has similar to KVCO. It also has a KDL as a VCDL gain, which is typically seconds per volt is the spec, right? And so it has its own dynamic range of delays to cover for the process variations, right? So so again, there are delays vary with the process and temperature for the same control voltage. So again, we should have enough control voltage range to meet the delay variation, to tune the delay variations across the process voltage and temperature. And again, these are the loop dynamics. Again, here also, again, it's a first order system because you don't have that integration, right? The phase to frequency integration. So it is inherently a first order system and it's quite stable, right? And here also we have the same, similar to the PLLs, right? So we have the opening transfer function, the loop bandwidth. We also here kind of take as a thumb rule of FF beta, and we follow here also. Again, we don't have any jitter accumulation here because it is just a delaying of input clock. We don't have it, we don't recirculate the clock and accumulate the jitter, right? And yeah, again, depending on the bandwidth, again, the settling time and the locking time of the DLL will have vary. So again, yeah, in a nutshell, like it's a more simplified version. It has a similar loop like a PLL, but it's not an oscillator. It's just a delay line we control with this. And we kind of use a lot of DLLs for multi-phase clock generation. Like let's say I have 360 degrees, right? I have 4 delay stages. I have to generate 6 stages. I have 6-stage delay line where I can generate phases 60 degrees apart, right? So this way we can have a very good multi-phase generation we can achieve. And again, there are some non-idealities, like for example, the large, on the layout, if you route also, right? These delay lines don't see same load as the very high frequency application that can be a very critical timing offset. So we kind of added dummy delays so that it mimics the scenario of the previous stage, or we have some delay elements added at the input of the PFD. So these are some of the techniques we call it boundary error correction. And but one critical issue with the PLL delay DLL is this delay variation, right? Sometimes it can lock to a harmonic, for example. So initially, if the delay of the delay line and the output of the delay line it exceeds the 2 clock cycles, because in the process and temperature it can vary, right? Then when the DLL corrects, it locks at the harmonic. So this is one of the things we need to watch out for, right? And we have to make sure, right, when we design the delay line across the PVT, the delay doesn't exceed the 2 clock cycles what we are achieving. Otherwise, it take corrective measures. Yeah, I think this is the last slide I had. So here we are seeing these are the analog DLL, right? Where we have analog control voltage, which very finely controls the delay, right? So that is forced delay stages will give 1 clock cycle delay, and each output will be 90 degrees out of 90 degrees phase apart. We generate the multi-phase clocks. We also use very commonly a digital configuration of a digital. It's a simple kind of a digital delay line, which is a series of inverters, right? And we have an n:1 multiplexer, right? And then we kind of detect the phase up and down, and then have a control logic, right? Again, it can be use some kind of averaging technique also here. We have the control logic and what is it? Sorry, and it chooses the particular phase, right? And we generate the clock out. So this is a very simple configuration. It's not as complicated to complex to design as the analog DLL, right? And we use a lot of times the DLL in a master slave configuration, as I explained in the memory interface, right? So the same delay line, we have replica delay lines across the die, right? And once we have a digital code, right, which corresponds to this 360 degrees phase shift, we just divide that digital code by 4 and give it to a multiple replica delay lines across the die, which need an exact 90 degrees phase shift. So this way we generate exact, for example, in case of a DDR application or so, we generate a exact 90 degrees phase shift, which is independent of process voltage and temperature. Yeah, so it looks simple, but there are a lot of non-idealities here which we need to take care. There could be jitter on the clock, noise on this, and because the reference clock has jitter, we need to do some filtering of that. We kind of do some kind of a averaging of the code in the control logic and give it to the multiplexer. That's kind of a digital filtering, right? Before we give it. So these are, yeah, there are some practical implications of that we can get into when you start designing it. But this is a very much simpler structure than analog DLL. So again, faster locking time, technology portability, because it's all the delay lines, very easy to port across the temperature, across the process. Noise immunity, because it's a digital code which you're giving for phase selection, right? So we don't have the control voltage, which needs to be very accurate or noise insensitive. And yeah, very low power and area. But one drawback is the resolution of the delay, right? What you can get, because it is determined by the inverter stage delay. But again, these days we get good picoseconds of delay. So again, the analog delay line can have very infinite resolution, to very picosecond accuracy. You can align that. Very finite resolution. So the resolution of the delay in a digital DLL will be much less than analog DLL. Yeah. Okay, I think this is all I had for today. Yeah, maybe I had to. Sorry, I had to rush through towards the latter half of the presentation, but yeah. So we can take any questions.
Actually, thank you, Pradeep sir. We have two questions
Mhm.
from the chat box. Mr. Guru,
Mhm.
what is the typical KO CEO we use?
Okay. typical KVCO we use is, again, the PLLs I have designed, I have kind of tried to use it something between 800 megahertz per volt to 1.2 gigahertz per volt for the kind of applications we are doing. So that is kind of a typical range. Around 1 gigahertz per volt is what is used. So if you are not able to do it, what we do is we divide. If the frequency range is very wide, what we do is, let's say I have a PLL which is required for 400 megahertz to 1600 megahertz, correct? Or then I have to use a very high KVC. Let's say I have only a 0.5 volts of control voltage range. Then what it ends up as a 2.4 gigahertz per volt as a KVC if you want to tune it. So that's again very sensitive and not good in terms of phase noise. So what we do is we have two banks of VCOs, right? We have two oscillators with some selection. So we depending on the frequency range you want to operate, right? We switch between the banks of the VCOs. So we design one bank of VCO within 400 to, let's say, 1200, and then again 1200 to 1600 or so with the same control voltage. So that's how we kind of keep the sensitivity low, at the same time meet the required frequency range within the required control voltage range. Yeah.
Please continue.
Yeah, thanks, Pradeep, for your answer. Actually, in recent some papers I even read they can go for some coarse frequency adjustment and
Yes.
fine frequency
Correct.
adjustment.
Yes.
Can you just explain about that one? Like, how do we do that?
Okay, so that's what the coarse tuning and the fine tuning, right? So what we do is, okay, let me take an example of a current stored oscillator. Okay.
Yeah.
So I don't have any material to show, but yeah, one way you do in the current stored oscillator, right? You have multiple current sources here, right? This is a V control I have shown, correct?
Yeah.
And I have, but I have shown it as a very simplified diagram, correct? So I have only control voltage direct and it's going to the bias current. But here I can also have a set of fixed biases. Okay, can I have a set of fixed biases, and on the fixed bias, I do the incremental current addition on top of that. So that fixed bias selection will give me the coarse tuning, and then this will give me the fine tuning in that range.
Yes. Yeah.
So if I go for this also, right, this frequency also, right, then first what I do for the minimum VCO, I do a frequency offset, go above that, and then I do a frequency tuning. I go up with frequency and go above that. So this is one technique we typically use. So we kind of offset it, and the same VCO ring we can use it for different frequency range.
Yeah, got it. Thank you.
Yeah.
Next question from Mr. Alok. In which applications ring oscillators are used or preferred?
See, most of the time by default, we try to use a ring oscillator only, because LC oscillator is, you need an on-chip inductor, right? And the process you are targeting should be an RF process which has this inductor support, that inductor modeling and all the behavior modeled, right? So we kind of, the first natural choice for us will be a ring oscillator. But with the ring oscillator, if I am not able to meet my phase noise requirement, then only I think about an LC oscillator, because LC tank needs an RF process, RF modeling, right? And also that comes with a cost, the large die area. But if my application is such that I have to meet a certain phase noise floor, right? I don't have a choice. I cannot achieve with the ring oscillator. Then I have to take a hard design call that I have to go with the LC oscillator. But by default, the choice is the ring oscillator. And another case is, it's a very high frequency. It may be I don't know about the current day, what the maximum uh, oscillator frequency that we are able to achieve in this to 5 nanometer or 3 nanometer process. But let's say these days you have applications with the 20 gigahertz, 25 gigahertz range kind of thing. So if you go with that kind of a high frequency, your ring oscillator, even if you go for a simple 3-stage ring oscillator, right, the propagation delay may not be sufficient, may not be low enough for hitting that frequency. And in those cases, we don't have a choice but to go with a LCVCO, right? So we go for, so the other way of putting this, we usually go for a ring oscillator unless I'm not able to meet the phase noise requirement and the jitter requirement, or uh, the frequency range is so high that my ring oscillator propagation delay cannot support uh, that frequency range. Okay.
Thank you. Thank you, Pradeep, sir. Apratim, please.
First of all, thank you, Pradeep, for the wonderful presentation. Actually, one thing I would say that we take clock for granted and voltage sources granted. Nothing comes granted.
Yeah.
It takes a lot of pain to get there.
Yeah.
So thank you. Pradeep, I have couple of questions. First
Mm.
question is, when we say that we are comparing at the first stage with the reference
Mm.
clock, right? That
Mm.
clock is a very low frequency,
Mm.
and I'm comparing that. I'm dividing it by n, right?
Yeah.
So any divisional error is kind of going to get accumulated, and then
Yeah.
in the end, in the long-term jitter, it will show up in the profile,
Correct.
right?
Yeah, that will be.
So that's one thing. So what we do to kind of make that, because that is another very big source of error, I believe, going to be. And my second question may be related to it, and also what Mr. Guru has asked, that we do a fine tuning and the coarse tuning
Mm.
of the V control, what you have told,
Mm.
right? So this is a trimming kind of a thing we do across process and
No,
all,
no,
or
no,
is it
no.
kind of a
You don't need
trimming?
to trim it, right? You don't need to trim it. See,
Okay.
the thing is, I'll come to that. So based on the division ratio, we can have some control logic inside and choose that static offset in the bias.
Okay.
That can be done. And yeah, coming to your question on the division ratio error, right? I think, mm, I mean, usually these are digital circuits, Apratim. So usually the digital dividers are accurate, unless uh, it's again subjected to very high noise or something where the clock gets corrupted. Correct. Uh, so that's where the division. So
Now, I believe because we are going to 20 gigahertz and all this application
yes,
with
yes.
from
Okay.
a
When we
megahertz.
go to the 20 gigahertz kind of
Yeah.
architecture, right?
Right.
We don't use the simple CMOS logic-based dividers. Actually, we have
Okay.
something called we use a semi-analog digital dividers. We call it as a
Mm-hmm.
prescaler and a modulus encounters and all that. So that again is a very uh, big area of research in itself,
Right.
right? So designing those dividers, because I don't think a conventional divider architecture would work with a 20 gigahertz kind of thing.
Correct.
Definitely. And you'd have that kind of division ratio, right? Everything low, like it's a 50 megahertz, for example. Right? So you
Correct.
have a divide by 400 or so. And again, as you said, there is not. So there are some specialty divider architectures which operate at a very high frequency. They are kind of the first few stages are analogish, right? And then we
Mm-hmm.
go to digital rail-to-rail kind of converter. Yeah.
And also the V control tuning or whatever we say, we can do it in different ways, but it's kind of a trimming we do, process trimming, or
No,
we kind
no,
of
no.
do a training kind of on the
It's
fly.
again, PLL is the feedback system, right? It adjusts itself. All we
Okay.
need to make sure that we should have the right programmability, right selection. The
Okay.
digital control bits you give, right? That you have to
Okay.
choose. And that is the register control, and it tunes itself. So that's what I said. It's a feedback system. It adjusts itself, but a lot of times it goes out of range, right? If the parameters
Mm-hmm.
are not, if you don't have the knobs for tuning the feed for itself to adjust, it can't. So what we need to do is we typically do a lot of programmability in charge pump currents, low filter characteristics, as I said, the VCO bank selection, the bias currents, right? So, right, so
Yes.
it's all about that. So, first silicon version, right? We do a lot of what do you say, programmability. when the silicon matures, we get a good yield and we see on the silicon the results are good, then we kind of tend to hardware if you want to save those parameter bits or make it less complicated. But yeah, these are kind of things.
Sure.
So a
Thank
lot
you.
of times we do, whenever we migrate to a new technology transition in an ASIC world, right? We do tape out certain test chips, right? This will be one of the IP that you put on a test chip, definitely. So we don't know because this particular generation how it works and how it correlates with the models and right in that technology before we start using it in a large scale ASICs. Yeah.
Also, oh, sorry, one more thing. So, have you ever faced something like a ground floor is itself shifting? That's why your V control, like the differential voltage is kind of unstable, like because it's kind
Yeah.
of a single-ended thing, right? But if your
Yeah,
ground itself is kind
yeah,
of
definitely. That ground bus will be there. So that's why we use a clean VSS for the
analog VSS kind of thing.
analog VSS kind of a structure. And again, as you said, I mean, it is a very simple representation, but if you go for a DLL, DPLs or a DDR application, so on and so forth, right? We always kind of use a fully differential V control voltage,
Yeah.
right? And again,
Thank-
differential V control voltage, and again, that has a lot of complexity, which fits into a charge pump because you need to have a common mode feedback circuit and all that. The charge pump, differential VCU. So yeah, again, yeah, these are like what I've just shown is just a first order thing, but yeah, definitely, yeah, I think ground, not only static phase shift, Pratim, even the noise, right? That goes
Right,
into the.
right.
So we definitely want to have a good isolation for all the critical components for the PLL and the silicon.
Thank you.
Dear participants, you can please unmute yourself and ask the questions.
Yeah, hi Pradeep, this is Guru. Actually, you told that mostly we try to use the ring VCO, right?
Yeah.
And I read there are multiple architectures for delay cells in the ring VCO.
Correct. Yeah.
Yeah. Generally in industry, like most of the people like adapted to like which kind of architectures for differential delay cell in the VCO.
Yeah, I have seen many using the current start VCO as a very popular choice.
Okay,
Correct?
I think this is single-ended, right? This one.
Yeah, this is a single ender. I think we have fully differential configurations of this also.
Okay.
Right? And also, right, so when you have a differential control voltage, we kind of not, you just don't bias like this. We kind of have a current steering kind of thing, right? Current steering kind of architecture, and we use it. Yeah. So, yeah.
Yeah. Thank you.
Hey, good evening, Pradeep. I mean, it has been a great summary and introduction. Do you want to make any comments or your insights about how substrate noise and package stress, especially in the high frequency VCOs, how do you handle? What are the impacts there?
Yeah. So substrate noise, a lot of time we put this VCO in a deep end well. Okay. So to isolate from the substrate noise, so we have a kind of, if the process approach a deep end, right? We have a deep end well or a deep end well guard ring kind of a structure. So that way we can isolate the oscillator, right, from the oscillator ground from the substrate noise. And to your one more question is in the packaging noise.
Package stress, yeah, especially in the plastic packages, you will have a lot of stress, which can cause electrical parametric shift in analog circuits, I mean components, and it can cause mismatches and that stuff.
Sorry, I don't have a specific answer for that. Maybe I can check and let you know in the forum. Yeah.
Yeah, we can catch up on that.
Yeah, sure. But yeah, again, as I said, right, like as you have pointed out, the PLL is as good as the environment, the performance, right? If it is in a noisy environment, there are a lot of
for example, most of your cases they're all plastic packages, right? Not hermetic or
yeah.
The final product is in a plastic package in a SOC context, not a standalone PLL,
yes,
right?
Yeah. Not as a component.
Yeah, more than even building, right? Even when it comes to substrate noise and package stress, more than the speccing of it, how do you analyze that pre-silicon that you are meeting? That
that's right. Then we have to have the proper modeling of the power source, right? Because your package RLC model, right? So, simulation setup, we need to model the noise source, the package RLC model and the noise source. And for example, you're keeping this PPP or DLL in a DDR kind of interface, for example, right? You have all the IOs switching right along with this, correct? So we have to have a good modeling of all the noise sources which can corrupt the PLL DLL supply, and we do the simulation. And as I said, the jitter also, right? We have, well, as I said, we have deterministic jitter and a random jitter, right? So we kind of do a jitter budgeting also. For example, like I have, for example, some 10 picoseconds RMS jitter I need to meet, 10 picoseconds jitter. About 100, eventually 100 picoseconds are peak-to-peak jitter I need to meet. I budget certain jitter for my supply noise component, certain budget for my random noise. And I try to simulate my PLL with all the noise components, supply noise components modeled, right? And noise profiles injected, and simulate the PLL and see the jitter. So that's how we, in a noisy environment, definitely, yeah, no matter what kind of isolation we provide, we definitely need to have a good modeling of the noises. That's a big challenge also, huh, right? To accurately model all the noise sources and inject them.
Yeah, maybe a quick question, Apartin, like given your background, like do you have any insights on the package stress aspects?
Currently, no, I don't have much insight on that package stress part.
Yeah,
We,
Apartin, you want to make any comments on that?
Yeah, Lakshman, I have less worked on PLL side, but I think from the NAND side, I can comment that we have a dedicated package team who gives the model, S parameter models and all. We plug it in our simulation, and as Pradeep told, like how good the packaging team giving us the model, it kind of help us to get those budgeting for the jitter and
Okay.
all. So that's
Yeah,
that's
maybe we don't need to answer them now. I'll just set the context, but we don't need to. I understand, given that we don't, all three of us
sure.
have.
And
And just
also
with the
one
problem
thing,
statement, we can
Lakshmanan,
discuss
maybe
later.
yeah,
yeah, maybe
So it's not.
catalog for a catalog business, it's kind of very important because kind of we are selling that component as an individual. For here, it is kind of like it comes with its own controller and the NAND die and all. So those things we get it like it becomes a little complex. So we make the system modeling as given by the team like that. Yeah.
Yeah, I will give a brief modulation to the context. Actually, I'm not talking about. I understand what you're saying. There is also electrical packaging. Basically, the packaging, the package interconnects and bond pads, etc. Right? That electrical model, RLC models getting is easier, and they are very, I mean, standard and very well known. What I was talking about is when you have a plastic package that's poured on top of it, it can cause a tensile and compressive stress on the entire
oh,
die.
okay.
So it will create a
Oh, okay.
gradient of stress gradient on the die,
Okay.
so that will cause mismatches and parametric shift.
Hmm.
Yeah.
Okay, you mean to say the mechanical stress
Yeah,
that you.
mechanical stress causing
Um,
electrical shift. As of now, today I know either
hmm,
in academics or industry, there is not much of electrical modeling
correct.
available today. So how do you handle it at high frequencies is the question.
Yeah,
This is one of the very uh, deep research areas, still potential for
definitely. I think
innovation.
yeah, I
Yeah.
appreciate that. Actually, yeah, even I, to be honest, even we also never thought of that kind of as you said, there is no proper modeling of that, like how a mechanical stress, what kind of gradients it causes on the die, and how the device parameters shift, right? Or even the both the passive and active elements parameters shift. So yeah, at this point, yeah, honestly, we are not I had that consideration so far in my experience. But again, yeah, as you said, it's a very critical aspect to be considered as we go to very tens of gigahertz of oscillators now. Yeah. So yeah,
Uh,
maybe yeah,
yeah, sorry for interrupting. We
yeah,
actually ahead of the time which you wanted to us.
yeah,
The questions can further take offline or
yeah.
they can ping to the organizing team for us. We'll
Okay.
share the questions to Pradeep sir. So
Okay.
can I share my screen?
Sure. Yeah.
Uh, just a second. Yeah. Thank you, Pradeep sir, again for accepting the invitation of IEEE CEDA Bangalore chapter.
Yeah.
It's a small token of appreciation from our CEDA Bangalore chapter, a virtual memento.
Yeah.
Thank you again.
Yeah. Thank you.
Yes, sir.
Yeah, thank you. Thanks for the opportunity. Good discussion, and maybe on some of the follow-up questions, I think you can share my email ID to the attendees. Maybe we can discuss over the email and see what more again.
Sure, sir.
Learn from
And,
each other.
yeah, I request everyone to switch on the cam so I can take one small group photo. Okay, guys, on a count of 3, 2, 1. I'll just take one more. On a count of 3, 2, 1. Yeah. Thank you all again for joining the Industry Insight series session. Thank you, Pradeep, sir.
Yeah.
And yeah, that's, we are wrapping up the session. Good night, everyone. Happy weekend.
Have a good day. Yeah.